Hi, good afternoon, everybody. My name is Liron, whatever you want to say. I work at Starkware. I'm in business development there. But I'm not here to talk about business development. Don't worry. I really wanted to keep this technical and more focused more broadly on layer 2s and validity rollups in particular. So keep me guided. Just for context, who here is familiar with ZK rollups? Okay, yeah, because it's an L2 day. I just never know where to go. What about who here has heard of Cairo? Oh wow, okay, cool. So you're pretty familiar with things are not like this 12 months ago. Okay, good. So I think the level of this discussion should be good for you. So let's get straight into it. So yeah, I wanted to talk about interoperability. Specifically, basically it'll be the talk will be successful if you sort of understand the possible architectures that you can do with bridging now that you have this prover verifier sort of architecture that ZK rollups or validity rollups enable. So I'm not going to be talking about traditional bridging mechanisms beyond a slide. I will be talking more about bridging using proofs and verifiers. Cool. And yeah, just talk a bit about StarkNet, mainly focusing on the prover architecture stuff. Should be revision for most of you, but I want to make sure everybody's on the same page. And then talking about different bridging mechanisms, storage proofs, and then some questions at the end. Feel free to ask questions throughout. I'll try do some time with them for questions. Okay, so StarkNet, the validity rollup, Eli Ben-Sasson, the founder of Stark, one of the inventors of Starks, is this whole ZK rollup terminology. He thinks we need to fight it and call things validity rollups. David Hoffman from Bankless wasn't familiar with this until he came to a StarkNet conference. So I'll say it to everybody else. ZK, in a strict sense, means formally preserving the privacy of the inputs. So like Zcash protocols. The ZK rollups that we talk about are not doing that. Aztec preserves privacy. The ZK rollups we talk about are doing validity rollups, meaning you're proving the validity of a bunch of transactions. So that's why I'm calling these validity rollups. The reason why, again, maybe revision for some, but making sure everybody's here on the same page, why do they scale these layer ones? Because verifying a proof is exponentially smaller than verifying the individual transactions in a proof. That is the magic of these innovations. You can have 6 million gas of transactions in a proof, and that represents tens of thousands of transactions. Instead of each node on Ethereum verifying tens of thousands of transactions, each node is verifying proofs. The math beyond that, of that is out of the scope of today. You're familiar with this? We developed Cairo, a smart contract language specific for, optimized for these ZK rollups. So the big feedback we get is, oh, you're not ZK EVM. The performance improvements you get from using Cairo are significantly better. These terms you might be familiar with. I was going to ask, have a quick survey of who knows these terms. I think if you know Cairo, you might know the other terms, you might not. They're not the focus of today's calls. But these terms are all I'd like to say they were started at Starkware, but others might disagree. Cool. So let's get into bridging. So the first most naive bridge is a simple trusted middleman. You can think of every centralized exchange as this. And we laugh a lot, but you'd be surprised by how many bridges in the ecosystem, even these cross-chain trustless bridges, effectively boil down to this. And they might say there's a multi-sig where no individual actually controls the funds, but you discover the multi-sig is controlled by 5 of people, the same person controls most of the keys, or 4 people who work in the same office control the majority of the keys. And that's effectively the same as this meme here. And there are some designs where you can decentralize this a bit. You can get people to stake tokens. They get slashed if they misbehave, etc. Those are all interesting mechanisms. Again, not the focus of today's talk. So today's talk is not talking about decentralizing or improving trust of traditional bridges. It's more like what did now the this proof of verify architecture enable because we have these proofs. So the next level, all the bridges now I present now are like unique to this proof of verifier architecture. This next level is if you want to send a message from Ethereum to, okay, I have Starknet here, but I really want to be true to my word at the beginning of the thing. Ethereum to any layer 2 ZK rollup. And this is live in production today, by the way. You can basically enforce that a message is only consumed on layer 2 if it's been sent on layer 1, which you don't, in the previous slide, you don't have that. Like in the previous slide, Sam can release your funds on the destination chain because he controls the private keys. Basically, with L1 to L2 messaging, you can enforce that the message can only be consumed in L2 if the initial message was sent from L1. Let me explain what's going on here. My animations aren't working because it's PDF. It's OK. So you can all hear me without the microphone, right? And let's just also describe the use case here. You want to deposit USDC from Ethereum to Starknet. Basic era. I really want to be as broad as possible. Oh, it's recorded. OK, great. Testing 1, 2, 3. Good. So you want to transfer funds from Ethereum to zk-SIG era, Starknet, any insert your L2, Tyco, Scroll. I really want to be agnostic here. So you send a message on layer 1, and that could be to the to an L1 dApp which says like USDC bridge, right? And then that dApp will send it to the Starknet core contract on layer 1. And then there's a node that listens to this and says, oh, you bridge 100 USDC on layer 1. I'm going to credit you that USDC on layer 2. Now that sounds like a typical bridge that we're not talking about today. So what's different here? When the L2 dApp consumes that message from L1, the next thing that happens now is the L2 dApp sends it to the L2 sequencer. And now the layer 2, as part of being a layer 2 and not a sidechain, generates a proof in the next batch of transactions. And in that proof, one of the things that is attested to is that the USDC that you basically minted for yourself on layer 2 corresponds to that layer 1 message that you received on layer 1. And and separate to that state update, you have this proof going on that the prover generates and sends to the verifier on layer 1. And the transaction is handled in the proof. So basically, let's talk it from layer 2's perspective. Layer 2's perspective, we say, you received 100 USDC. We generate a proof that attests that you indeed minted for yourself 100 USDC. When the verifier verifies that proof, the verifier says this proof is only valid because it corresponds to an L1 message that you first sent that USDC to yourself to the contract on layer 1. If we would mint this USDC for you on layer 2, even if you are Jeremy Allaire from Circle, it doesn't matter who you are, even if you are Starkware, even if you control all the keys in the world, the proof that's sent to layer 1, will not be progressed. The verifier will say, I cannot verify this proof as being valid because I don't have a layer 1 message that corresponds to what you're trying to do in layer 2. This architecture doesn't exist with traditional bridges, and it's also it's one of these benefits of being a layer 2, not just a sidechain. So the L2 cannot consume the message without the L1 event. Like if the L2 would try and get your USDC, what would happen is the next proof that's submitted to layer 1 would be like, this proof's invalid. This doesn't work. We cannot progress the state of layer 2. And I want to emphasize here, there are no trust assumptions here. Like you're trusting cryptography, not economics. This is one of the beauties of ZK rollups in general. But specifically here, even if you control the prover, even if you control the prover, you can't do anything. As long as you trust, meaning you trust the cryptography in the audited verifier on layer 1, doesn't matter how good your math is, the proof will not be verified on layer 1. Doesn't matter who you are. The one caveat in what I just said is what's one issue with this bridge? Who's going to actually mint your tokens for you on layer 2? Maybe the sequencer on layer 2 will censor your transaction on layer 2. So you can extend this to say, it's a bit advanced, but you can extend this to say, if the proof that gets sent to the verifier within the next few proofs does not include this minting of the asset on layer 2, then somebody gets slashed. Then you can introduce economic incentives to discourage censorship resistance. That's a bit advanced. So that is, layer 1 to layer 2. And again, the proof sort of validates the integrity of this mint on layer 2. Let's discuss the other direction. You want to bridge funds from layer 2 to layer 1. One use case for layer 2 to layer 1 is something called DeFi pooling. So we're roughly 100 people in this room. We each have $200 in savings. If we would deposit that in a DeFi protocol in layer 1, we're each paying $40 in gas fees, whatever it is. Not worth it. We're losing 40%. But now we each come pool together. We have $20,000 in funds now. We're happy to pay the $40 gas fees. So, and we can aggregate those funds on layer 2 and then send them to layer 1. One use case for layer 2 to layer 1 messaging. So this is the next bridge we're talking about. What happens here is layer 1 will only consume that message together with the proof. It's actually easier than, we should have started with this design because it's easier than layer 1 and layer 2. Basically, when we do this DeFi pooling example, we've said, hey, we have 20,000 USDC we want to deposit in Compound. Compound on layer 1 will only consume that message once the proof from layer 2 comes. Until that proof comes, it says, I'm not trusting any middleman who will send this message to me. But then once that proof comes, there's an automatic approval, confirmation that that message did indeed come from layer 2 because, hey, it's in the proof and the state update that's together with this proof. So there's two things happening. You send a state update saying, hey, we want to deposit 20,000 USDC from layer 2 to layer 1. We have the proof attesting to that state update. And then boom, trustlessly in the sense that there are no trust assumptions, the message can now be consumed on layer 1. Again, here the only risks are censorship resistance, which happen in any blockchain, and the economic incentives there of receiving your fee payment are protection from that. That's layer 2 to layer 1. Next, and then some comments on this. I think I said these. Layer 1 cannot consume the message without the layer 2 event, and you don't even need any safeguards from this. The layer 2 event comes first. The securities in cryptography, not in economic incentives. Now, some people say, well, hang on, currently you're doing a proof every few hours, not every few minutes or every few seconds. And what if I want to do my layer 2 to layer 1 message immediately? You can also reduce, firstly, one comment about this is the reason why, this is also a bit of a misnomer in the industry. The reason why the proofs are every few hours right now is because the gas costs on Ethereum for verification. It's not because of the latency of generating a proof. Latency of generating proofs is coming down and parallelizable. We parallelize these ourselves, and zkSync also do it, basically everybody does. They're stateless, so you can parallelize as many as you want. The reason why we do it every few hours is because even the gas on Ethereum to verify is cheap on a per transaction level. It's still, if you reduce that latency, you still end up paying more gas. So it's just a trade-off, and as more activity picks up, that latency goes down. But what you can do is you can have liquidity providers say, I know that this will come in the next proof, so I'm going to release the funds now. You can also register the fact on layer 1 before the proof comes. There are some cool designs to do this while also reducing latency. The next thing I want to talk about is shared proofing. Okay, so I think Polygon zkVM, zkSync, Starknet, everybody's basically announced this sort of architecture. Polygon's announcement last week really focused on this, but it's a natural step, and it's not even with every innovation, once the innovation is out, it's oh yeah, that makes sense. So let's say you have an app chain future that already exists. So you have Starknet running as a public network. You have an app chain, which is its own dedicated instance of Starknet. You might have ZK Sync Era even. You might have some spot trading app chain, whatever. You generalize this, but the point is that each of these are individual siloed blockchains. All of these running as layer 2s on top of Ethereum. What you can do with these is that they all use the same individual proof that is sent to Ethereum. Not the same prover, the same proof. So Ethereum receives a proof confirming the state transitions of all these chains are valid, but it's a single proof sent to Ethereum in one go. So I'm confirming I have $100 here, and the latest proof, you're confirming you have 100 ETH here, etc. Or let's actually talk about this with bridging. I actually want to bridge 100 USDC from this app chain to Starknet, okay? Now, because we're using a shared proof, when we do this through recursive proving, there's a thing called SHARP, shared prover. The idea is that the proof confirms those two legs in the exact same atomic proof on Ethereum. The one leg being I'm basically burning the 100 USDC here, and the second leg that I'm minting the 100 USDC here. And then, once that recursive proof is generated, all of that's off-chain, it gets sent to the verifier in one transaction, and that verifier verifies atomically both legs, the burning and the minting. So there's no trust assumptions here. The trust is in the cryptography of the proof arriving on layer 1. Once layer 1 verifies this, it says, I can confirm, yes, indeed, in this last batch of transactions, there was a burn and mint in the same batch. And you can even extend this to say, my burn on this chain will only be valid if there's a corresponding mint on the other chain. And again, sorry for the repetition, but the security here is through cryptography, not through economics. Now, there's a latency of the proof generation, which some people will be happy to do. You're basically ensuring that both legs happen and are confirming the same proof. So basically, yeah, the transfers in one atomic proof. The proof confirms both legs. And not just both legs, that there was a burn and there was a mint, but that burn was only valid because there was a corresponding mint on the other chain. And you can even, you basically do this thing that, like, hang on, if the fact on the other chain was not registered, then return my funds to me. Another elegant thing, and again, without this whole proof of verify architecture, it wouldn't be so viable. Cool. The next thing is like the ultimate boss is storage proofs. Anybody familiar with storage proofs? A few hands. Yeah. Each level gets filters more and more and more. So a few prerequisites. You can think of Ethereum as just like a database. Like whenever you run a website, you query some data from a database, and then you can present it in the front end. Ethereum could be the same thing, meaning you want to know the state in Ethereum 2 years ago in order to do some NFT mint for some users. You want to do it in order to do some collateral for some DeFi app on your layer 2. Just look at Ethereum as a database in that sense. Now, because of the way that blockchains, a chain of blocks, because of how they work, once you know the block hash for like block 1000, you can deterministically work out not just the block hashes of all the blocks previously, but also the accounts, the Merkle tree of the account balances and transactions. All those trees are deterministic because of the nature of the one direction of the hash functions. So now you can, with those assumptions, you can generate what's called a storage proof of the historical data. Basically, you say, if you're telling me that the hash of block 1000 on Ethereum is A, B, C, D, I can prove to you that the hash of block 2, like 998 blocks previously, was 1, 2, 3, 4. Now that is a lengthy proof if you're just like doing that proof by yourself. Okay, I'll talk about the architecture in the next slide. Let's talk about use cases of this. I can now confirm that, hey, Vitalik's ETH balance 900 blocks ago was 100 ETH. When all I have, the only starting point I have is the block hash of the latest block. And for governance purposes, I can know your ERC20 balance in order to vote for some governance vote. And you can even do some advanced stuff of like, tell me my average token balance over 1,000 blocks, or for some sort of criterion for receiving an NFT, etc. You can get super crazy with this. But what I haven't talked about is the scalability of this. So let's talk about how this works. Basically, you give me the block hash for block 1000. I can generate a storage proof confirming like all of the details from previous blocks before then. But then I can take this a level deeper and wrap this around a Stark or Snark proof, or insert any validity rollup sort of proving mechanism, and generate a validity proof testing to this. Basically, given that the hash of block 1000 was ABCD, I generate a proof that Vitalik's ETH balance 998 blocks ago was 100 ETH. And that's all off-chain and cheap and parallelizable. That's proof generation classic on the cloud, off-chain. And then I can send the statement to the blockchain, and the blockchain can verify this validity. Basically, you say, given this input, the ETH balance is 100, 900 blocks ago, please verify it. Ethereum trustlessly verifies this proof, the securities and the cryptography, and everybody's happy. And you have tremendous gas savings from doing this if you're doing this for multiple queries. If you're doing for one person's ERC20 balance, you're probably better off not wrapping this around a proof. But if you're doing for more advanced stuff, then it's worth it. I've got a few minutes to talk about use case. Yeah, I want to talk about one use case, governance votes. So what's the problem today? Let's say you got like 400 uni tokens. You got their airdrop like 2 years ago, and you want to vote in something. So if you do that all like fully trustlessly on layer 1 Ethereum, you're paying like $15 in gas fees to vote, which if you're a retail user, you're not going to do that. On the other side of the spectrum, you can use like solutions like Snapshot, which is purely off-chain, which take a snapshot of balances of uni at a certain block and say, vote off-chain by signing that you indeed own this public address that had this balance. But then you're trusting the Snapshot team or those like that to aggregate all of these votes. Using these storage proofs, what you can do is wrap all of this around a ZK proof of the storage proof. So basically, there's a storage proof confirming all of our balances of uni tokens historically at a certain checkpoint. We all sign a transaction saying we want to vote for or against this proposal. And there's a validity proof that gets sent on chain that says two things. Firstly, we attest to all of these balances of these ERC20 tokens at the time, and also how each of you voted in that vote. And then that storage proof that's in this ZK proof is sent to Ethereum, where it's verified, and then the governance progresses based on that. Other stuff, yeah. With bridging also now, you can suddenly generate a storage proof of some sort of state on chain 1 in order for chain 2 to access it without actually bridging the items. Cool. There's a team not affiliated in any financial sense, but they're building this on Starknet called Herodotus. It was not paid, but they don't even know I'm presenting it. But I just thought if I'm talking about it, I'll mention their names. And they actually have an API you can go and play around with. They're in Paris this week as well. So let's just summarize everything. We went through like 5 different levels. Trusted bridges are bad. Even if multi-sigs, you need to check each individual multi-sig to see how they're implemented. L1 to L2 messaging, we talked about how the L2 message can only be consumed if the next proof that comes from L2 to L1 includes that, it corresponds to that L1 message that originally sent. Going from L2 to L1, the same thing but the other direction. The proof that's sent from L2 to L1 will confirm exactly what you want to send to L1 and then progress the state. We talked about using shared proofs where multiple different app chains or blockchains all use the same atomic proof in order for you to like burn on one chain and mint on the other. And then we ended with these storage proofs, which were just described. I'm doing great with time. The whole ecosystem is vibrant with cool stuff. You can go and have fun here. Any questions?
You said that the proofs are atomic. What do you mean by that? Should you mean the transactions?
Good question. What I meant, I mean, maybe my English is wrong there, very possible. He asked, I said that proofs are atomic. What do I mean? What I mean is that there's a single proof that includes the transactions on chain 1 and on chain 2. So an atomic proof in the sense that transactions on different chains are included in the single proof. That's verified. So let me go to the... Oh, where are we? Here we go. On chain 1, you do a transaction. Chain 2, you do the other leg of that transaction. The verifier in Solidity is verifying a single proof. And that single proof has both legs of that bridging transaction. So maybe I mean single proof, not atomic proof.
Doesn't this mean that the
So he asks, what are the risks involved if the receiving rollup consumes this transaction before it's settled? So in that sense, if you want to be super strict, you can wait. Like the receiving rollup can only recognize your transactions, if you want to call it that, once the proof is sent to layer 1. In a practical sense, what happens is you can take on the risk for those next few hours until the proof arrives. Every product can choose to do that or not do that. And then if the proof wouldn't arrive, you basically revert to the state that happened before both legs of the bridging transaction happened. So in that sense, I mean, it'd be a big mess. There'd be bigger messes besides this individual bridging transaction if like the proof wouldn't arrive. But basically, if the proof wouldn't arrive, you revert back to the last state you ever knew before any proof was submitted. One more question, maybe?
So nothing's final until it's committed onto the final proof on Solidity. But what if, say, Starkware took out a $500 million loan and said, no worries, it's going to be included in the next block, we'll give you the money, and then never commits the block, you know?
Yeah, so he asked, basically, similar to the previous question in the sense, what if people assume that a proof will arrive on layer 1, but it never arrives? What are the risks involved there? Maybe the final question, then I'll end. What if, like I do a $500 million withdrawal to a centralized exchange, and then the proof never comes? So I'll answer this with what happens on Bitcoin, like unrelated to proofs and verification. If you send to an exchange some BTC to sell, some exchanges will say, I will credit this BTC immediately before there's even a single confirmation because I see it in the mempool. Other exchanges will say, I will wait 3 blocks. Others say, I will wait 6 blocks. Others say, you know what? For $5,000, I will wait 0 blocks. I'll see it in the mempool. For $1 million, I'm going to wait 6 blocks. And in that sense, it's the same thing here. So people in the industry are happy to basically transact on the layer 2 before the proof arrives on layer 1. But you could have these different levels of like, hang on, you're moving $100 million, let's wait for the proof to arrive on layer 1. And I think that's where things will end up reaching an equilibrium. Cool, we'll end there. Thank you.
Thank you, Liron.